Okay, so we'll take a look at an example. This one says use a graphing, a calculator graphing tool. So that would be something like Desmos, some of the online things, or you could use a graphing calculator as well. And I'll show you what we need to do. So we have a function, sine of x over x, and we want to find a delta so that the limit, as we're approaching, so the limit is 1, so we want to basically show that as the function approaches 1 in the y direction, when that is really small, then we're also very close in the x direction to 0, to x being 0. So the way that we would do this is we would say, okay, the function is sine of x over x, and we want that to be, we're looking at the difference between that and 1, and we want that to be small. So we set up this thing. I mean, it literally is coming, as you can see, right from this top part right there. And then we just set up an inequality. So sine of x over x minus 1 needs to be less than 0.01 and greater than negative 0.01. So this is an absolute value inequality. And this is how we do it. So now what we'll do is we will just add 1 to both sides. So what we find when we add 1 to all 3 sides is that we have this. And so the idea here in using a graphing calculator is you have 2 options. So I'll do this one. So what you would want to graph is you'd want to graph your function, f of x equals sine of x over x. And then you want it to be between these 2 constants. So those 2 constants are just constant functions, which are, straight across like this on a graph. So you'd want to graph g of x being 0.99. You'd want to graph h of x being 1.01. And when you put those 3 things onto a graphing calculator, or onto like Desmos, you're just trying to see where does f of x intersect with g of x or h of x. So I'm going to cut this video and show you what that looks like graphically right now. So for the problem where we're trying to find out sine of x over x minus 1, absolute value less than 0.01, what we looked at was this idea of sine of x over x, and then we want it to be greater than 0.99, less than 1.01. So what I want you to see here is that the red function is the sine of x over x, and then we have y equals 0.99, y equals 1.01. Those are just constant functions. And all we need to do to figure out that distance is take a look at how far we are, basically those intersection points of the function with those 2 constant functions. So notice it's pretty small. So I'm going to zoom it in here so that you can see it easier. So hopefully you can kind of see what's happening here. Desmos is pretty powerful. I can, take us to 0.9 if I wanted to. Maybe that helps us a little bit. And if I take it to like 1.1, so this might help, right? It's just a different view. But hopefully what you see here now is that the sine of x over x intersects here and here. So all we need to figure out is what is that distance from here to 0, which is the same as what it's going to be. There's just symmetry here from here to 0. And what's nice about Desmos is I can just go like this, and notice it kind of is showing me that there's an intersection point, and it's going to tell me what it is, the 0.2453. And then of course, if I were to come to the other side, I can see that intersection point as well. It's going to tell me negative 0.2453. So either way, we have that distance from 0 being the 0.2453. And so that's what tells us that we want that as our delta. So for any student that might be thinking, well, do I have to use the 0.99 and the 1.01? Is it possible to see it more in that sine of x over x minus 1? And you can see that that's what I have over here. It's the first function, sine of x over x minus 1. And then I have that first inequality, the negative 0.01 and the positive 0.01. And that function looks different than what we just saw. But if I zoom it in, zoom, 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 zoom. We're still seeing the sine of x over x minus 1, that's the red one. And you see that we have two constants there as well. They're just, this thing is basically just in a different area because of the different values. But if we go and think about the intersection, we take a look, and here we go. We have the same value over here. And over on the other side, we have that same value as well. So no difference whether you want to do the first inequality, the second inequality. The idea there is they are equivalent, and they're still going to give us that same distance of the 0.2453. And now we're back. And so what we learned from what we saw graphically, was that we want that delta to be 0.2453. And at that value, you can, on either side, you're always going to have that absolute value being true as long as delta is that distance. So now we can say that tells us that when x minus 0 is less than 0.2453, this is what this is telling us, then our function f of x minus the distance between that and the limit is going to be less than 0.01. So we're going to look at one last problem, and this one is, as you can tell, how is it different? Take a look at this limit. So we're taking ourselves back to this idea of proofs. Take a look at that. As you probably noticed, that is quadratic. So it's done a little bit differently. This is the highest level thing that we're going to do with this. But we do know it's a parabola, it's nice and smooth and continuous. And of course, if you plug in 3, you'd have 9 plus 3 minus 5, and you'd get 7. So we do know that the limit is 7. We just want that precise inequality. So we're going to start out very similar. So we want those things in the x direction, x minus 3, absolute value, greater than 0, less than delta. And then we want our function minus its limit to be less than epsilon. So no difference there. We have our scratch work. So this is where things change just a little bit. But obviously, as you can see, it's still very similar. So we're going to take this x squared plus x minus 5 minus 7, and we want that to be less than epsilon. That's our goal here, again, because of this. And we have x squared plus x minus 12. And so similar to the two proofs that we did, but not exactly the same, as you can tell, we still can't factor this. This has the ability to factor. We have a trinomial here. So why don't you see if you can factor that? Okay, so now we're here. And things that we want to kind of remember is, and this, this would probably, I think, come back from trig or even geometry. So it may not be super familiar to you, but basically if you have those things in the absolute value being less than epsilon, then that is the same as splitting them apart. That's still going to be less than epsilon. So I believe that's like the triangular property, something like that. Let me know if you want me to find it, because I'm sure I have it somewhere. All right, so we have this. So you might notice, oh, we have this absolute value of x minus 3. We have it right here. That looks familiar to us from the problems that we did before. And so the key thing to see there is, the key thing to see here is, what we need to do is we need to bound that, right? Because we don't have that same thing that we had before. We don't have, absolute value of x minus 3, some number multiplied by it that we can just divide by. Now we have this absolute value of x plus 4. But we need to bound the absolute value of x minus 3 because of the fact that that's what we're approaching, and that's, what we need to base our delta off of. So what I'm going to do is I'm going to come over here, and I'm going to write the absolute value of x minus 3. And what is kind of the most like wondrous part of this is what we can do to bound it is we can just choose any delta. And I know that seems crazy, but so let's say we choose delta equal 1. And the reason we do that is because you could actually pick any value of delta. Obviously, smaller is good because you're trying to, be able to say that something is true because something else is true. That we always want, let's say we always want delta to be less than 1. Or to be 1 so that this is always less than 1. So we let delta equal 1 and then we have this. And then what we do is we bound this. And the way we bound it is just by using the fact that it's an absolute value inequality and then solving for x. So the idea here, by adding 3 to both sides, is that if delta equals 1, then the absolute value of x minus 3 is bounded so that x has to be between 2 and 4. That's the only way that that absolute value of x minus 3 is going to be less than 1. So now that we have this, what we can do is actually then bound the other piece that we have, this absolute value of x plus 4. So the way that we do that is now we want to know, well, if x is greater than 2 and less than 4, what would x plus 4 be? So now we can add 4 to each of those pieces. And that tells us that x plus 4 has to be between 6 and 8. Okay. So then that tells us, now that we have that x plus 4 has to be greater than 6, less than 8, then that means the absolute value of x plus 4 is always going to be less than 8. So we want to pick the bigger of the number and bound it. And the reason that we do that is because we want to know what is x plus 4 always going to be less than. And so it's always going to be less than 8. And then what that does is that now that we have bounded x plus 4, we can now take what we just got from that to give us, of course, that number that we're looking for so that we can have the absolute value of x minus 3 being less than something that then gives us a delta. So there's a little bit of variability here in terms of what people could pick for the delta over here that would give them here, but because you can do the formal proof, it still works no matter which delta you choose. So you could have chosen 0.1, 0.01, you could get as small as you want. You're still going to be able to bound that x plus 4, and then you're still going to be able to use the value for the last piece of this. So now we're ready for the formal proof. So we're going to let delta be the epsilon over 8. Now, here is the last part that has a tendency to make students go, what? So remember, the whole thing here was we were trying to find a good choice for delta. But in trying to figure out what a good choice for delta would be, we said, well, let delta equal 1. And by letting delta equal 1, we were able to basically find this value that delta could also be, which could be smaller than 1, and in general it will be, but we need to consider both of those. So here's kind of an exciting piece, which is that we're going to let delta equal the minimum, this is math notation here, between 1 and epsilon over 8. So of course we did not need to do this with the linear ones, but we need to do this now. And again, it's because we earlier decided that delta was 1, and then we used that fact to come up with the fact that the absolute value of x minus 3 is less than epsilon over 8. So as long as we have the minimum of either one of those, and again, typically it would be epsilon over 8 because that's going to be a lot smaller, then we're going to have what we need. So that's why we do that. So we are still kind of in our normal pieces here. We've got our x squared plus x minus 5 minus 7. This is still the same. X squared plus x minus 12. And then that is going to be equal to x, absolute value of x plus 4 times the absolute value of x minus 3. And then, as we have already kind of picked up on, we know that the absolute value of x plus 4 is less than 8, and the absolute value of x minus 3 is less than epsilon over 8. So this is going to be less than 8 times epsilon over 8. Okay? And that, of course, is equal to epsilon. So we have just shown that the function and its limit, the distance between them is less than epsilon anytime the absolute value of x minus 3 is less than delta. So as long as x minus 3 is less than delta, then f of x at minus 7, difference between that absolute value is less than epsilon. And we have now just shown that our limit as x approaches 3 for this quadratic is 7. And that is section 1.7.